Welcome, and thank you for joining this session. Over the next 2 hours, we will work through a single big idea together, that where a person lives shapes their health in ways that are tangible, measurable, and most importantly, addressable. This lecture is built from a book chapter titled Strategies to Address the Needs of Underserved Communities, a Geospatial Information Systems Analysis of Dual-Enrolled Populations, written by Angel Reyes, a Doctor of Public Health candidate and Master Certified Health Education Specialist at Claremont Graduate University. The chapter sits at the intersection of health economics, public health, and geography, and it was written for graduate students encountering geospatial methods for the first time. You do not need any prior training in geographic information systems to follow along. What you need is curiosity about a simple puzzle. Two people can carry the same insurance card, live the same distance from the same hospital, and still have profoundly different experiences getting care. Why? Answering that question requires new techniques, new frameworks, and a new way of thinking about research design, and that is exactly what this session teaches. By the end, you will be able to sketch a basic geospatial research project from research question through analysis. Let us begin by looking at how the session is organized. Before we dive into content, here is how the next 2 hours are structured. The lecture is divided into different sections. We start with why geography matters for health, then move to the foundational techniques of spatial analysis, then to 3 theoretical frameworks for understanding access to care. From there, we cover how to design a geospatial research project, the classic fallacies that can quietly break a spatial study, and the data privacy obligations that come with location data. We finish with a full case study that ties every piece together. Each major section ends with a short knowledge check. When you hear a question, pause the audio, think or write your answer, and then resume to hear the explanation. Scattered throughout are pause and try exercises that invite you to apply an idea to a community you know personally, because spatial thinking becomes real when you attach it to streets and bus routes you have actually traveled. A roadmap slide opens each section, so you always know where you are in the larger argument. Everything in this session comes from a single chapter, so you are absorbing one well-structured argument deeply, rather than a whole field at once. Let us look now at what you should be able to do by the end. Every good research design starts with a clearly defined outcome, and every good lecture should too. The 5 objectives on this slide come directly from the chapter, and rather than read them back to you word for word, let me describe the arc they form. The first 2 objectives are about understanding. You will describe how geospatial analyses integrate perspectives from multiple disciplines to conceptualize place-based health, and you will explain the role of geographic factors in pursuing equitable care across diverse communities. One is methodological, the other ethical, and together they answer why this work matters. The third objective is about judgment, evaluating how spatial variables interact with the research design's inherent assumptions. Spatial data does not simply plug into a standard study design, it changes what the design assumes, and you will learn to spot those changes. The fourth objective is the most ambitious and the center of this session, designing a basic geospatial research project from research question through analysis. We will walk that path with a 5-question protocol and then watch it play out in a full case study. The fifth objective closes the loop, assessing how visualization techniques communicate spatial findings and their meaning. Maps are arguments, and you will learn to critique them as such. Every knowledge check today is written against these 5 objectives. Now let us see the road ahead. Here is our roadmap for the full session, and it mirrors the logic of the chapter itself. Section 1 builds the motivation. We meet the population at the center of this chapter, people enrolled in both Medicare and Medicaid, and see why geography, not insurance, becomes the key to understanding their disparities. Section 2 is the toolbox. 7 foundational techniques like buffer analysis and network analysis that let researchers turn location into data. Section 3 brings in theory. 3 frameworks that give structure to the question of why people do or do not get care. Section 4 is the heart of the session, a 5-question protocol for designing a geospatial research project. What, where, who, why, and how. Section 5 is the warning label, the fallacies unique to spatial research and how to defend against them. Section 6 covers data privacy, because location data can identify people, and protecting the community you study is a non-negotiable obligation. Finally, Section 7 is a complete case study, diabetes management among dual enrollees, that follows one researcher through every phase we have discussed. You will see this roadmap again at the start of each section, with our position highlighted. With the map in hand, let us begin Section 1. Welcome to Section 1, Why Geography Matters. Every field has a founding observation, and for this chapter, it is a simple one. Having health insurance does not guarantee having health care. Coverage can be identical on paper, while access differs dramatically on the ground. In this section, we will meet the dual enrolled population and see why it is so informative for isolating geography. Walk through a thought experiment with 2 identical patients in one hospital. Define what a geographic disparity is and connect it all to the built environment. By the end, you will be able to explain why studying healthcare access requires geography. Let us start with the reality of limited resources. The chapter opens with a statement worth sitting with. The reality of our world is that there are limited resources, distributed non-uniformly, resulting in differences in access to care, despite having health insurance that affords the care. Let us take that apart. Healthcare resources, meaning clinics, hospitals, physicians, pharmacies, and transit routes that reach them, are finite, and they are not spread evenly across the landscape. Some neighborhoods are dense with providers, others have almost none. Now add insurance to the picture. Insurance is a financial instrument. It affords care, meaning it removes or reduces the cost barrier. But affording care and reaching care are 2 different problems. A person can hold an insurance card that covers a specialist visit completely and still be unable to get to that specialist because the specialist is far away, the bus does not run there, or the journey is unsafe. This is the gap the chapter targets. By studying how the distribution of resources influences health outcomes, researchers can begin to understand how equitable care can actually reach the communities that need it. Notice the shift in the research question this implies. Instead of asking who has coverage, we ask where care physically is and who can realistically get to it. That question is inherently geographic. It cannot be answered from an insurance enrollment file alone. It requires knowing locations, distances, routes, and neighborhoods. And that is why this chapter exists. But to study geography cleanly, we need a population where the usual confounders, income and insurance status, are already controlled. That population is up next. The chapter focuses on a specific population, individuals who are dual enrolled, meaning they are covered by both Medicare and Medicaid at the same time. Why this group? The answer is methodological, and it is elegant. Think about what normally makes health disparities hard to study. When you compare 2 communities and find different health outcomes, dozens of explanations compete with each other. Maybe one community is wealthier. Maybe one has better insurance coverage. Maybe both. Income and insurance are powerful confounders that muddy almost every comparison. Dual enrollees largely take those two confounders off the table. Because eligibility for this combined coverage is tied to financial circumstances, dual enrollees offer a greater control on income level compared to the general population. Everyone in the group is in a broadly similar economic situation. And because every member holds the same two-part coverage, Medicare plus Medicaid, insurance status is effectively held constant as well. So when we observe that two dual-enrolled communities experience different health outcomes, we cannot blame the difference on one group having better coverage or more money. Something else must be at work. The chapter's argument is that a large part of that something else is geography, where these individuals live, what surrounds them, and what they can reach. By controlling for income and insurance through the choice of population, the chapter isolates and emphasizes the effects of geographic factors, letting each community's unique disparities come into focus. Keep this logic in mind throughout the session. Whenever the case study returns to dual enrollees, it is leaning on this same design choice. Now let us make geography concrete with a thought experiment. Here is the thought experiment at the heart of this chapter, and I want you to picture it vividly. Two identical individuals live exactly 10 miles from the same hospital. Same age, same health, same coverage, same distance. On a traditional data set, these two people are indistinguishable. Now follow each of them out the front door. The first person owns a car. 10 miles means perhaps 15 minutes on a highway, door to door. The second person depends on public transit. 10 miles might mean a walk to a bus stop, a wait, a transfer downtown, and over an hour of travel each way, with fare to pay in money and time. The chapter names the factors that distance alone does not account for: travel time, transportation cost, neighborhood safety, and other barriers to accessing care. Think also about land use, a factor the chapter's take-home points highlight. Highways that cut a neighborhood off, one-way streets, the availability of parking. 10 miles as the crow flies tells you almost nothing about 10 miles as a patient travels. Here is why this matters for research, not just for empathy. If your model treats these two individuals as identical, the differences between them do not disappear. They hide. The chapter calls these masked geographic factors, and they are plausible confounders that threaten a study's internal validity. Your results become biased in ways you cannot see because the variable driving the difference was never in the model. The remedy, which we will develop in Section 2, is to geospatially enrich the data, capturing the variation in travel time so a bus rider and a car owner stop looking identical. First, though, let us give this phenomenon its proper name. Let us now define the central concept precisely, because careful definitions are what let researchers measure things. A geographic disparity is a difference in care that is associated with where a person lives, rather than with other attributes like citizenship or wealth. The chapter describes it as an unavoidable difference, unavoidable in the sense that the individual cannot simply opt out of it. You can carry your insurance card anywhere, but you cannot carry your neighborhood's clinic supply, bus network, or road layout with you. Notice how this definition builds directly on what we have established. With dual enrollees, wealth and insurance status are already controlled. So when a difference in care persists between two dual enrolled communities, the definition points our attention at place itself. The address, not the person, becomes the explanatory factor. This is a genuine shift in how we think about disparities. We usually describe disparities in terms of who people are, their race, their income, their age. A geographic disparity says, hold the person constant, change only the location, and watch access change. Think back to our two identical individuals and their very different 10 miles. That is a geographic disparity in miniature. Everything that follows in this session, the techniques, the frameworks, the design protocol, exists to detect, explain, and ultimately reduce these disparities. The natural next question is where they come from, and for that, we turn to the social determinants of health. Where do geographic disparities come from? The chapter grounds its answer in a concept you have likely met before, the social determinants of health, abbreviated SDOH. These are the non-medical conditions that shape health outcomes, and one of their recognized domains is the built environment, the human-made surroundings in which people live, the streets, buildings, transit systems, and land use patterns of a community. The concept of place as a health factor arises directly from this domain. Here is the crucial historical point. Built environments that produce disparities did not appear by accident. The chapter notes they can often be traced back to historical policies like redlining or unjust land use. Redlining systematically starved certain neighborhoods of investment for generations. Decisions about where to route highways, where to permit industry, and where to build housing shaped which communities got clinics, parks, and reliable transit, and which did not. A neighborhood's present-day lack of providers is often the long shadow of a policy written decades ago. Now layer on the population we are studying. For dual enrollees, these historic barriers compound with two additional burdens. First, limited insurance acceptance. Not every provider accepts their coverage, which shrinks the already thin supply of reachable care. Second, mobility-limiting morbidities. Many dual enrollees live with conditions that make travel itself difficult, reducing their ability to independently access care. Notice the word compound. These are not separate problems standing side by side. They multiply each other. A distant clinic is a bigger barrier when fewer clinics accept you, and walking to the bus is painful. This layered picture is exactly what our analytical frameworks in Section 3 will help us organize. But first, let us preview the chapter's 5 take-home points. Before our first knowledge check, let me give you the chapter's own summary of itself. 5 take-home points that we will keep returning to all session. Point 1. Every community has its own unique story of health disparities, and researchers use geographic factors to make those lived experiences tangible and quantifiable. Geography turns stories into evidence. Point 2. Learn to think beyond singular straight lines. Miles to a hospital may not capture someone's actual journey, because variation exists in traffic, transportation cost, and land use, things like highways, one-way streets, and parking. You already know this one. It is our two individuals thought experiment. Point 3 introduces something new that we will develop fully in Section 6. Researchers who combine geographic factors with health data must be well-versed in small cell suppression and geomasking techniques, because location data generates new risks of reverse data engineering that could identify the very patients in your study. The map that reveals a community can also expose an individual. Point 4 follows directly. When planning a geospatial research project, the researcher must strike a healthy negotiation between data granularity and data privacy, keeping the analysis meaningful while protecting the study population. Detail and protection pull in opposite directions, and managing that tension is a core design skill. Point 5 states the purpose of it all. The goal of a geospatial research project is to illustrate how a community is impacted by its built environment, so that interventions can have place-based specificity. We do not map disparities to admire the problem. We map them so that the response, a new clinic, a mobile unit, a transit change, lands exactly where it is needed. Hold on to these 5 points. Now, let us check your understanding of Section 1. Time for our first knowledge check. I will ask 2 questions. After each one, pause the audio, formulate your answer out loud or on paper, and then resume to compare. Question 1. Why does this chapter choose dual enrollees, people covered by both Medicare and Medicaid, as its focus population for studying geographic disparities? Pause now and give your answer. Here is the reasoning we covered. Dual enrollees provide a greater control on income level and insurance status compared to the general population. Because everyone in the group has broadly similar financial circumstances and identical two-part coverage, those 2 powerful confounders are effectively held constant. Any remaining differences in access between dual-enrolled communities cannot be explained by money or coverage, which lets the effects of geographic factors stand out clearly. If your answer mentioned controlling for income and insurance so that geography is isolated, you have it exactly. Question 2. 2 identical individuals each live 10 miles from the same hospital. Name at least 3 factors that straight-line distance fails to capture about their journeys to care. Pause now. Welcome back. The chapter lists several: travel time, transportation cost, and neighborhood safety, plus land use features such as highways, one-way streets, and parking. You might also have said mode of transportation, a bus versus a personally owned vehicle, which is the example we will carry into Section 2. Any 3 of these earn full credit. If both answers came easily, excellent. You have the motivation of this entire chapter secured. If they were shaky, consider replaying the last few slides, because everything ahead builds on them. When you are ready, join me in Section 2, where we open the Geospatial Toolbox. Welcome to Section 2. Section 1 established why geography matters. Now we shift from motivation to method. This section opens the Geospatial Toolbox, 7 foundational techniques that turn raw location data into evidence about access to care. From drawing a simple buffer around a clinic to producing a color-coded map of an entire region. None of these techniques is complicated on its own. The power comes from combining them, and by the end of this section, you will see how a few simple operations, chained together, tell a rich story about how access differs from one residential area to the next. We begin with the idea that motivates all of these tools, a process called geo-enrichment. Recall our 2 identical individuals who each live 10 miles from the same hospital. Distance alone does not account for travel time, transportation cost, neighborhood safety, or the other barriers standing between a patient and care. If our data set records only distance, all of that variation stays hidden. Here is why that matters methodologically. These unaccounted factors are not just missing detail, they are plausible confounders, variables that may influence both where people live and the outcomes we measure. Suppose the bus rider misses more appointments than the driver and their health worsens. A model that sees only distance will conclude that 2 people with identical access had different outcomes, and it will go hunting for an explanation in all the wrong places. The real driver of the difference, the 90-minute bus journey, sits invisibly outside the model, quietly biasing every estimate it produces. When confounders lurk outside the model this way, they threaten the study's internal validity, meaning we can no longer be confident that the effects we estimate are real rather than artifacts of what we failed to measure. Researchers address this problem by geospatially enriching their study. Geo-enrichment means attaching new, location-derived variables to each record in the dataset. For our 2 individuals, geo-enrichment captures the variation in their travel time, so the researcher can account for differing modes of transportation, such as riding the bus versus driving a personally owned vehicle. The same 10 miles might mean 20 minutes for one person and 90 minutes, 2 transfers, and a bus fare for the other. Once that difference lives inside the data set as a variable, the model can see it, adjust for it, and estimate effects more honestly. Geo-enrichment is the why behind everything in this section. The 7 techniques we are about to meet are the how. Each one either creates a spatial variable, joins spatial data together, or displays spatial patterns. Let us survey the full toolbox, then examine each tool in turn. Here's the complete toolbox, presented as Table 1 from the chapter. Take a moment to read it on screen rather than listening to me recite it. What I want you to notice is how the 7 techniques fall into 3 natural families. The first family, measures, buffer analysis, proximity analysis, and network analysis each create a spatial variable, whether that is who lives within a chosen radius of a clinic, how far a patient must travel, or how long the journey takes along real routes. The second family restructures data. Spatial join uses location itself as the key that combines separate datasets, and dissolve merges small areas into bigger ones so that datasets at different scales can meet. The third family communicates. Overlay analysis finds places where multiple barriers to care stack up, and choropleth mapping turns columns of numbers into color patterns a reader can grasp at a glance. At an individual level, these techniques are the foundation for more thorough and complex geospatial research projects. Combined, they reveal spatial relationships and patterns that might otherwise be labeled independent events. Over the next several slides, we walk through each family in turn, starting with the measurement tools. Let us begin with the 2 simplest measurement tools, buffer analysis and proximity analysis. They sound similar, but they answer different questions, and choosing between them is often the first design decision in a study. A buffer analysis draws a circle around a location of interest. Imagine placing the point of a compass on a clinic and sweeping a 10-mile radius around it. Everything inside that circle is the buffer, and the purpose is to discover who resides within that radius. A buffer starts from the facility and asks, which residential areas fall within reach of this location? It is a supply-side question about coverage. Proximity analysis works in the other direction. It measures the distance between 2 points of interest, typically a patient's residence and a source of care, to determine how far patients must travel to obtain care. Proximity starts from the person and asks, how far away is help? Here is a way to keep them straight. If your question begins with a place, you likely want a buffer. If it begins with a person or a population, you likely want proximity. Both techniques share the same limitation we flagged earlier. They measure straight-line geometry, and a straight line of 10 miles can conceal enormous differences in the actual journey. That is exactly the gap the next technique fills. Network analysis is where geospatial measurement starts to resemble a real human journey. Instead of drawing circles or measuring straight lines, network analysis calculates transportation time along actual routes. Its purpose is to compute the travel time and the route a person would realistically take to reach a point of interest. Why does this matter so much? Think back to the take-home points from the start of this lecture. One of them urged us to think beyond singular straight lines, because miles to a hospital may not fully encapsulate someone's journey. Variation exists within traffic, transportation cost, and land use. Things like highways, one-way streets, and parking. A straight line cannot see a river with only one bridge. It cannot see that the bus route detours through downtown, or that a highway makes a distant clinic faster to reach than a nearby one. Network analysis can. For dual enrollees, this technique is especially consequential because many members of this population do not drive. Network-based travel times are what let us separate the bus rider from the driver on the previous slide, and that separation is precisely the variation our models need. Network analysis is how travel time stops being an assumption and becomes a measured variable. With measurement in hand, though, a new problem appears. The travel times we compute live in one dataset, and the health records we care about live in another. Getting them to talk to each other is the job of the next two techniques, spatial join and dissolve. Measurement tools create variables, but a study also needs its datasets to talk to each other. That is the job of the restructuring family, spatial join and dissolve. A spatial join uses location to combine separated datasets. In ordinary data work, you join tables on a shared key, like a patient identifier. A spatial join uses geography itself as the key. If one dataset holds enrollee health records with addresses, and another holds neighborhood characteristics, the spatial join matches each enrollee to the neighborhood that contains them. The purpose, as the chapter puts it, is to combine enrollee health data with the geographic factors of the neighborhoods they live in. This is the mechanical heart of geo-enrichment. It is literally how a health record acquires a travel time, a provider count, or a transit measure. But joins only work when the two datasets share a common geographic scale, and often they do not. That is where dissolve comes in. Dissolve removes the boundaries between small areas so they become bigger areas. Picture a map of individual residential parcels. Dissolving them merges those many small shapes into a single neighborhood shape. The purpose is to transform residential level data into neighborhood level data so that a spatial join becomes possible with a dataset reported at the neighborhood scale. Notice the workflow forming here. Dissolve adjusts scale, and spatial join merges information across datasets at that shared scale. Keep dissolve in mind because it returns later in this lecture as a privacy tool as well, since aggregating upward can protect individuals from being identified. With our data measured, merged, and sharing a common scale, the remaining task is to see and show what it contains. That is the job of the final family, overlay analysis and choropleth mapping. The last two techniques in Table 1 are about seeing and showing patterns. First, overlay analysis. An overlay stacks multiple map layers on top of one another and identifies areas with co-occurrences. Its purpose is to identify places where multiple barriers to care pile up in the same area. Imagine one layer showing areas with long travel times, another showing areas with few providers, and a third showing areas with limited transit. Where all three layers darken at once, you have found a community facing compounded barriers, exactly the kind of place where a geographic disparity concentrates. A single variable map could never reveal that stacking. Second, choropleth mapping. A choropleth map turns numerical values into color patterns, shading each geographic unit according to its value. Its purpose is to reveal numerical outputs in a color-coded system as opposed to a standardized table. This may sound like mere presentation, but do not underestimate it. Recall the fifth learning objective of this chapter, assessing how different visualization techniques help communicate spatial findings and understand their meaning. A table of 200 neighborhood travel times is technically complete and practically unreadable. The same numbers as a shaded map instantly show where burden clusters, where it fades, and where the boundaries of disparity run. Policymakers, community partners, and fellow researchers can all read a map. Together, overlay analysis and choropleth mapping close the loop of the toolbox. We measured with buffers, proximity, and networks. We restructured with dissolve and spatial joins. Now we can see and communicate what the data says. Individually, each technique answers a narrow question. Combined, they reveal spatial relationships and patterns that might otherwise have been labeled independent events. Let me walk through the chapter's own example of this composition. Start with a buffer analysis. We draw a 10-mile radius around a hospital and identify all the residential areas that fall inside it. At this point, every one of those areas looks equal. They are all within 10 miles, so a naive analysis would say they all have access. Now add a network analysis. For each residential area inside the buffer, we extract the actual travel time to the hospital along real routes. Suddenly, the picture fractures. One area sits beside a highway and reaches the hospital in 15 minutes. Another, the same distance away on paper, requires an hour by bus. A third has no direct transit route at all. Together, these two techniques tell a story about how access differs from one residential area to the next. And that sentence deserves emphasis because the chapter is explicit about it. This difference in access to care is the core concept of the entire chapter. Everything that follows, the frameworks, the design questions, the fallacies, and the case study, is in service of measuring, explaining, and ultimately reducing that difference. Notice also what happened methodologically. Two simple operations, composed thoughtfully, converted an undifferentiated blob of coverage into a ranked, quantified portrait of disparity. That is the craft you are learning. Before we move on, let us make this concrete with a short exercise. It is time for our first pause and try exercise. Pause the presentation after I describe the task and give yourself 3 to 5 minutes. Here is the prompt. Think of a clinic, hospital, or pharmacy in a community you know well. Maybe it is where you grew up, where you live now, or where you have worked. First, write a buffer question about it, something like, who resides within 2 miles of this clinic? Choose a radius that feels meaningful for your community. Second, write a network question that deepens the buffer question. For example, for the people inside that radius, how long does the journey actually take by bus, on foot, or by car at rush hour? Third, and this is the important part, name at least one thing the straight line distance hides in your community. Perhaps there is a freeway with no pedestrian crossing, a bridge that bottlenecks traffic, a bus line that stopped running on weekends, or a neighborhood people avoid walking through after dark. When you resume, reflect on this. The thing you just named is a candidate spatial variable. If you were geo-enriching a data set for your community, that hidden factor is exactly what you would want to capture, because it is a plausible confounder that distance alone would mask. You have just performed, informally, the first act of geospatial study design. Go ahead and pause now. When you return, we will check your understanding of the full toolbox with a short knowledge check. Let us check your grasp of the toolbox with 3 questions. I will read each one, then pause briefly before giving the answer, so feel free to pause the presentation if you want more time. Question 1. A researcher wants to identify areas where long travel times, low provider supply, and limited transit all occur in the same place. Which technique fits? The answer is overlay analysis. Overlay stacks multiple layers and identifies areas with co-occurrences, which is exactly what finding compounded barriers requires. Question 2. A dataset contains residential level records, but the neighborhood dataset the researcher needs to join is reported at a coarser scale. Which technique prepares the residential data? The answer is dissolve. Dissolve removes boundaries between small areas so they become bigger areas, transforming residential level data into neighborhood level data so that a spatial join becomes possible. Question 3. A published study reports the bus travel time from each residential area to the nearest dialysis center. Which technique produced those numbers? The answer is network analysis, because only network analysis calculates transportation time along actual routes and can reflect a specific mode, like the bus. Proximity analysis would only give straight-line distance. If you answered all three correctly, you have the toolbox well in hand. If any felt shaky, remember the three families: buffers, proximity, and networks measure; joins and dissolves restructure; overlays and choropleths reveal. With the tools secured, we now need theory to guide how we use them. That brings us to Section 3, the frameworks for analyzing access to care. Welcome to Section 3. We now have a toolbox full of techniques, but tools alone do not make a study. If you can measure travel time to every clinic in a state, which travel times matter, and which barriers should you model first? Answering those questions requires theory. This section introduces three frameworks for analyzing access to care. Anderson's behavioral model explains health service utilization through broad determinants. Penchansky and Thomas measure access along 5 specific dimensions, the 5 A's. And the Cultural Adaptation Research Framework explains why patients may not use care even when it is objectively available. These three are not competitors. They form a sequence from broad classification to specific measurement to real behavior. Let us start with why frameworks matter at all. A framework provides a structured lens for examining access to care so that others may build upon a shared foundation. That sentence from the chapter contains 2 distinct benefits, and both deserve a moment. The first benefit is structure for you, the researcher. Access to care is a sprawling, multi-dimensional idea. Without a lens, a geospatial study becomes a fishing expedition, mapping variable after variable and hoping something interesting appears. A framework tells you which factors to look for, how they relate, and what a finding would mean. The second benefit is a shared foundation for everyone else. When you declare that your study operationalizes accessibility in the sense of Penchansky and Thomas, other researchers immediately understand your choices, can compare your results to theirs, and can extend your work. Science accumulates through exactly this kind of shared scaffolding. This chapter uses 3 frameworks in a deliberate sequence. Anderson's behavioral model classifies the factors behind health service utilization into 3 broad determinants: predisposing, enabling, and need, which lets an analysis focus on one determinant at a time. Penchansky and Thomas offer the 5 A's: availability, accessibility, accommodation, affordability, and acceptability, which add more specificity and give us measurable dimensions. Finally, the Cultural Adaptation Research Framework, abbreviated CAR, assesses care-seeking behavior when both geographic and financial means are met, explaining the puzzle of people who could reach care but do not. Using all 3 allows the researcher to start broadly and progressively narrow to the specific dimensions preventing dual enrollees from accessing care. Let us take each framework in turn, starting with Anderson. Anderson's behavioral model is a framework used to explain health service utilization through 3 determinants called predisposing, enabling, and need. Let us define each one carefully. Predisposing factors are individual characteristics, the attributes a person carries with them that shape their inclination to seek care before any question of resources arises. Enabling factors are the available resources to obtain care. These are the means, the practical supports and conditions that make seeking care possible. And need factors focus on how much demand the care requires, the severity and urgency of the health condition itself. A useful way to remember the trio is as 3 questions. Who is the person? What resources surround them? And how sick are they? Now, here is the key insight for our purposes. The most relevant factors for a spatial analysis are the enabling factors because they reflect a person's built environment, what is actually available to them where they live. A clinic within walking distance is an enabling factor. A bus route that connects home to a provider is an enabling factor. The presence or absence of these resources is written into geography, which means our toolbox from Section 2 can measure them. A buffer analysis counts enabling resources within reach. A network analysis quantifies how enabled or disabled a person's journey to care really is. Anderson gives us the conceptual category, and the geospatial techniques give us the ruler. On the next slide, we apply this model specifically to dual enrollees and see how their enabling factors divide into 2 distinct kinds. Let us bring Anderson's model home to our focal population. For dual enrollees, the chapter tells us their enabling factors divide into either family-based or community-based factors, such as transportation assistance or family caretakers. Consider what this means concretely. A dual enrollee with an adult daughter nearby who can drive them to appointments has a family-based enabling factor. Their access to care flows through a personal relationship. Another enrollee with no family in the area may depend on community-based factors instead, a transportation assistance program, a paratransit service, or a clinic reachable by bus. Same benefit coverage, same medical need, yet very different enabling structures, and only one of the 2 is visible on a map. This is worth pausing on. Family caretaking is largely invisible to geospatial data, while community-based enabling factors, transit lines, assistance programs, clinic locations, are exactly what our techniques can capture. A thoughtful researcher keeps both in mind, using spatial data for what it can see and remembering what it cannot. Before we move to the second framework, note the contrast the chapter draws. A difference between this framework and Penchansky and Thomas is that Anderson's behavioral model explains utilization conceptually, while the other measures access to care through 5 dimensions. In other words, Anderson tells us what kinds of forces are at work. The 5 A's hand us a measuring instrument. When you need to classify and theorize, reach for Anderson. When you need to quantify and compare, you need the 5 A's, which is where we go next. Penchansky and Thomas disaggregate the single word access into 5 measurable dimensions, each conveniently starting with the letter A. Let us define all 5. Availability captures the supply of providers. Are there enough physicians, clinics, and services to meet the population's demand? Accessibility focuses on reachability. Can patients physically get to the care that exists, given where they live and how they travel? Accommodation centers on the organization of care. Do the clinic's hours, appointment systems, and intake processes fit how patients actually live and work? Affordability is cost. Can patients pay for care, considering charges, coverage, and their resources? And acceptability is about patient fit. Do patients feel comfortable with the providers, and do providers welcome these patients? Notice what disaggregation buys us. Saying a community lacks access is a diagnosis too vague to act on. Saying a community has adequate availability but poor accessibility, plenty of providers that people cannot reach, points directly at transportation, not at recruiting more physicians. Each dimension implies a different intervention, and confusing them wastes resources. Try the distinction on a familiar situation. A dual enrollee lives near several clinics, but the appointment lines are long and the front desk cannot accommodate a caretaker's schedule. The providers exist and the routes exist, so availability and accessibility are met. The failure lives in accommodation. Working through cases like that one is how the 5 dimensions stop being vocabulary and become an instinct for diagnosis. For spatial research projects, the chapter is specific. Availability and accessibility are the primary focus, as they deal directly with supply distribution and route access. You can hear our toolbox in those words. Availability is what a buffer analysis counts when it tallies providers within a radius. Accessibility is what a network analysis measures when it computes travel time along a bus route. The other 3 A's, accommodation, affordability, and acceptability, matter greatly, but they live mostly in schedules, prices, and perceptions rather than on maps. Next, we apply the 2 spatial A's to dual enrollees. For dual enrollees, the chapter highlights a crucial complication. Both spatial dimensions can co-occur, appearing together as low provider supply combined with limited public transportation to the clinics that do exist. Think about what that combination means for a real person. There are few providers in the area, so the nearest participating clinic is far away, and there is limited transit, so even that distant clinic is hard to reach without a car. Each barrier alone would strain access. Together they compound, and this is exactly the pattern an overlay analysis from Section 2 is designed to expose. Multiple co-occurring barriers concentrated in the same area. The compounding also carries an intervention lesson. Fixing only one dimension may not help. Recruit more providers into the area, and residents without transportation still cannot reach them. Add a bus route to a market with no providers, and the bus has nowhere useful to go. Compounded barriers demand solutions that address both dimensions, or carefully sequenced ones. But now comes the caveat that opens the door to our third framework. The chapter observes that despite cases where availability and accessibility are both met, patients can still underutilize services due to a bounded rationality that influences care-seeking behavior through incomplete knowledge or previous experiences. Sit with that puzzle for a moment. The providers exist, the routes exist, the map says access, and yet utilization stays low. Distance and supply cannot explain this. We need a framework that understands how people actually decide, with limited information and personal history. That framework is the Cultural Adaptation Research Framework. Next. The Cultural Adaptation Research Framework, abbreviated CAR, explains that a patient will satisfice their care rather than optimize it because of their limited information, time, and experience with what is available to them. Let us unpack the word satisfice, since it carries the whole idea. To optimize is to survey every option and select the best. To satisfice is to choose the first option that seems good enough and stop looking. Optimizing assumes complete knowledge and unlimited time. Real patients have neither. In practice, this means patients seek care from only a fraction of what is objectively available to them, guided by subjective beliefs about what exists in their community. There may be 12 clinics within reach, but if a patient knows of 2, their world contains 2. Notice that nothing about this is irrational. Given limited information, time, and experience, stopping at good enough is a sensible way to navigate life. The error would be ours as researchers if we modeled patients as optimizers, because the map we draw and the map a patient carries in their head are two different documents. For dual enrollees, these perceptions form from what their community has historically offered, shaping perceived utility in the quality of care available and in what feels realistically reachable. A neighborhood that spent decades underserved teaches its residents not to expect care nearby, and that lesson outlives the shortage itself. Here is the striking consequence the chapter draws. Despite objectively equal access, two identical dual enrollees may utilize care differently, purely because of their own unique bounded rationality. Geography has been held constant, and behavior still diverges. So what does Carr prescribe? It addresses bounded rationality by acknowledging that interventions and health systems must adapt to a patient's cultural or linguistic barriers, expanding what is perceived as available and acceptable. The system moves toward the patient, not the reverse. A clinic that offers services in a patient's language does not just accommodate, it enters that patient's perceived map of options. With all three frameworks now on the table, the next slide assembles them into a single working sequence. Let us step back and assemble the three frameworks into the single strategy the chapter intends. Using all three allows the researcher to start broadly and then focus on the specific dimensions preventing dual enrollees from accessing care. Picture the sequence as a funnel. At the wide top sits Anderson's behavioral model. It classifies everything that could influence utilization into predisposing, enabling, and need factors, and it points the spatial researcher toward the enabling factors, the resources written into the built environment. Anderson tells you where to look. In the middle of the funnel are Penchansky and Thomas with the 5 A's. They take that broad territory and disaggregate it into measurable dimensions, and for spatial work, they focus us on availability, the supply of providers, and accessibility, the reachability of that supply. The 5 A's tell you what to measure, and Section 2 gave you the tools to measure it. At the narrow bottom of the funnel is the Carr framework. It handles the cases the map cannot explain. Patients whose availability and accessibility look fine, but who still underutilize care, because bounded rationality means people satisfice among the options they perceive rather than optimize among the options that exist. Carr tells you why behavior departs from the map, and it reminds you that interventions must adapt to patients. Broad determinants, specific dimensions, individual behavior, context to conduct. Notice too that the funnel mirrors how research actually proceeds. Classification decides where measurement is worth the effort, and measurement decides where behavioral explanation is still needed. When you design your own study, you will likely move down this funnel in order, and in Section 4, we will do exactly that through 5 design questions. First, a knowledge check. Time to test your command of the 3 frameworks with 3 scenarios. As before, I will read each scenario, pause, and then explain the answer. Pause the presentation if you want longer to think. Scenario 1. A research team is beginning a study and wants to organize every possible influence on health service utilization into broad conceptual categories so they can decide which category their spatial data can best address. Which framework fits? The answer is Anderson's behavioral model. Classifying factors as predisposing, enabling, or need, and then focusing on one determinant is exactly what Anderson provides, and the enabling factors are the natural home for spatial analysis. Scenario 2. A team wants to quantify 2 things for every neighborhood in a region. the supply of providers, and the travel time required to reach them, and then compare neighborhoods on those measures. Which framework? The answer is Penchansky and Thomas and the 5 A's. Provider supply is availability, and reachability is accessibility, the two dimensions the chapter identifies as the primary focus of spatial research. Scenario 3. Two dual enrollees have objectively equal access, same supply, same travel times, yet one uses services regularly and the other rarely does, apparently because of what each believes is available and trustworthy in their community. Which framework explains this? The answer is the Cultural Adaptation Research Framework, whose account of bounded rationality and satisficing explains why utilization diverges even when access is equal. If you matched all three, excellent. You now hold both the tools and the theory. Section 4 puts them to work designing an actual research project. We have covered the foundational techniques and the 3 frameworks for thinking about access to care. Now we move from concepts to craft. How do you actually design a geospatial research project? The chapter's answer is a protocol of 5 guiding questions. What outcome are we studying? Where does that outcome concentrate? Who lives within that concentration? Why does the concentration occur there? And how did this pattern develop over time? These 5 questions give you a repeatable structure for almost any place-based health problem. Keep the frameworks in mind because they return when we reach the why question. Before we walk through each question, we start with the single most important design shift that separates geospatial research from every other study design you have learned: the way we treat location itself. Here is the fundamental shift. In a non-geospatial study, location is just another attribute of the study population, like age or sex. You might record a participant's county the same way you record their birth year, and then you move on. In a geospatial design, location becomes a contextual factor in its own right. Place is promoted to an independent variable, something you believe actively shapes the outcome, rather than something that merely describes the participant. Think about what that promotion means. If place actively shapes health, then the neighborhood is no longer background scenery for your study. It is one of the forces your model must explain, and that has consequences. Once you acknowledge place as an independent variable, you must account for geographic boundaries, geographic scales, and the geospatial techniques you apply, because every one of those choices will influence the estimated effect on your dependent variable. Draw the boundary at the county instead of the neighborhood, and your estimate changes. These design choices can introduce bias, just as design choices do in any other study. The difference is the source. In geospatial research, the source of potential bias is primarily spatial. It lives in how you drew the boundaries, how you set the scale, and which techniques you used to enrich the data. That is a new category of methodological risk, and it deserves the same care you would give any threat to validity in a conventional study. The 5-question protocol we are about to walk through exists to help you manage exactly this risk. It turns each spatial choice into a justified decision, rather than an unexamined default. Let us look at the 5 questions as a set. This table lays out the full protocol, and rather than read it to you, I want you to see its shape. Read down the first column, and you can hear the logic of an investigation unfolding like a funnel. You begin wide with an outcome worth studying, something like underutilization of preventative health services. Then each question narrows the aperture. Where locates the outcome on a map? Who introduces you to the people living inside the pattern? Why builds an explanation for the pattern? And how traces the history that produced it? Notice that the sequence is not optional. Each question depends on the answer before it. You cannot ask who lives in the concentration until you know where the concentration is, and you cannot explain why it occurs until you know who it affects. Notice, too, that the examples in the right column trace a single thread, from geocoded records of diabetes burden to the population traits and historical investments behind it, which previews the case study waiting at the end of this lecture. Over the next 5 slides, we take each question in turn and unpack the rationale, the methods, and the decisions each stage demands. We start where every research endeavor starts, with the what. Every research endeavor begins with an outcome that is worth improving, something with a clear societal or financial benefit. Reducing the prevalence of chronic diseases is the kind of outcome the chapter has in mind. But notice that worth improving is doing real work in that sentence. You are not just picking a topic that interests you. You are identifying a problem whose improvement would deliver measurable benefits for society. At this stage, the outcome is defined through exploration. You might approach the problem quantitatively, digging into surveillance data, or qualitatively, listening to community members describe their experiences. The chapter is agnostic about which door you enter through. What matters is that the process refines a broad concern into a worthwhile outcome with measurable benefits. Then comes a step that students often skip. To validate the outcome, you should collaborate with a transdisciplinary team and consider competing outcomes of interest. Why does this matter so much? Because no single field can comprehensively examine a multidimensional issue like healthcare access. An economist sees cost structures. A clinician sees disease progression. An urban planner sees land use. Each of them might propose a different outcome as the most worthwhile target, and hearing those competing proposals sharpens your own. Maybe you arrive convinced the outcome is hospital readmissions, and a colleague persuades you that medication adherence is the more measurable and more actionable target. That conversation is the validation. Once the outcome of interest is defined, the project moves to data collection and to geo-enriching the data set so you can visualize how the outcome concentrates across space. That brings us to the where. The where stage is where your project meets reality. This is the stage that consumes your time, your energy, and your grant funding, because acquiring data and geo-enriching it for area-based attributes is expensive in every sense. And here is the first hard truth. Datasets are rarely perfect. You will open the file you fought to obtain and discover missing variables, gaps in coverage, and fields that almost but not quite measure what you need. The chapter offers 2 coping strategies, each with a price. The first is proxy data, finding a variable that replicates the missing one. The second is imputation, using statistical methods to estimate missing values. Imputation can fill the holes, but it introduces uncertainty into the model, and that uncertainty can become bias. Every value you fill in is a guess, and every guess you feed the model quietly shapes what the model believes. Neither strategy is free, and the chapter is candid about why you need them anyway. These limitations reflect the realities of research, where grant funding is limited, data sets are incomplete, and your energy is divided across projects. Designing well means designing within those constraints, not pretending they do not exist. Then comes a step specific to spatial work. After completing the dataset, visualization should occur at multiple scales. Why multiple? Because aggregation and disaggregation can mask the very variation your study exists to find. A pattern that is invisible at the county level may be dramatic at the neighborhood level, and a pattern that looks strong at one scale may dissolve at another. If you only ever look at one scale, You never know what the other scales are hiding. Look at your data zoomed out and zoomed in before you commit to a unit of analysis. Once the outcome is mapped and a scale is chosen, the natural next question is who lives inside the pattern you found. Determining the scale shifts the focus to a new question. Who resides within the geographic unit you have chosen? The map from the where stage showed you a pattern. The who stage introduces you to the people living inside it. The method here is comparison. By examining the geographic unit's variation of interest, you can start to make meaningful comparisons that are geographically driven. The chapter-specific move is worth slowing down for. You compare high-burden areas together, areas that share a heavy burden of the outcome but differ in their composition of factors. Imagine two neighborhoods, both with high rates of poorly managed diabetes. One has low vehicle access but plenty of clinics. The other has clinics that are technically nearby but almost no public transportation. Both express the same burden, yet the ingredients differ. By comparing across areas like these, you can identify the traits most often associated with the outcome of interest. Maybe vehicle access keeps appearing wherever the burden is high. Maybe it is comorbidity load, or the age structure of the residents. These associations matter because they may lead to explanatory factors, the mechanisms at play that contribute to the health burden. Notice the careful language. At this stage, you have associations, patterns of co-occurrence, not proof of cause. But associations are the raw material of explanation. They tell you where to point the theoretical machinery you built in the framework section. And that pointing is exactly what happens next, because identifying who shares the burden leads directly to the stage that asks why the burden occurs at all. Let me start this stage with the warning every methods course repeats, because the chapter repeats it too. Association does not establish causation. The traits you identified in the who stage are correlates, not confirmed causes. But association offers an important starting point for formulating a model that explains why the outcome occurs. And that is the work of this stage. How do you keep an explanatory model honest? You ground it in theory. This is where the frameworks from earlier in the lecture earn their place. Anderson's behavioral model, Penchansky and Thomas with their 5 dimensions of access, and the cultural adaptation research framework each tell you which variables plausibly matter and how they relate. The frameworks ground the model in theory so you can develop the most relevant specifications, rather than throwing every available variable into a regression and hoping. After the model is specified, something genuinely exciting becomes possible. You can build counterfactuals to answer what-if scenarios by hypothetically modifying geographic barriers. What if travel time to the nearest clinic dropped by half? What if a new transit route connected this neighborhood to that hospital? The model lets you rehearse these interventions mathematically before anyone spends $1 in the real world. Notice what the counterfactual really is. It is the same model you specified, run again with one geographic barrier hypothetically modified, so that the difference between the two runs becomes your estimate of the intervention's effect. That is why the specification work mattered so much. A counterfactual built on a poorly specified model rehearses a fantasy. Now, the chapter is honest about the limits. The result is an estimation plagued by practical and political uncertainties. Real interventions face budgets, zoning fights, and elections that no model captures. Yet even so, counterfactual modeling may remain the most feasible way to model population-level interventions before they are attempted. You cannot randomize a highway. Simulation is often the best rehearsal available. One question remains in the protocol. If barriers explain the burden, where did the barriers come from? That is the how. The final question in the protocol looks backward. This stage examines how the pattern formed over time by analyzing historical policies and any reforms to understand their potential effects. Why does history deserve its own stage in a research design protocol? Because understanding the origin of a health burden changes what you expect an intervention to accomplish. A pattern rooted in historical policy reflects a compounded effect across generations, and the chapter is blunt about the implication. A short-term intervention is less than likely to immediately fix it. Think about what compounding means here. A policy decision about where to route a highway or which neighborhoods received investment does not just affect the people alive when the decision is made. It shapes the built environment those people's children inherit, and their children after that. The chapter connects this directly to the social determinants of health. The compound effect is observed through the built environment domain, as each generation is born into an inherited community. Nobody chooses the infrastructure they are born into. They inherit it, along with whatever barriers it contains. This is also why the chapter returns, once more, to collaboration. Disentangling health burdens that originate from historical policies governing infrastructure and land use requires transdisciplinary collaboration. A health economist alone cannot read zoning history. A historian alone cannot specify a spatial model. Understanding and addressing persistent barriers takes both. And with that, the 5-question protocol is complete. What, where, who, why, and how. This thought process prompts the design of a geospatial research project, but the chapter immediately adds a caution. Before you run anything, you must know the fallacies that bias spatial models. We will meet them shortly. First, let us make this protocol yours. Time to put the protocol in your own hands. Pause the presentation for about 5 minutes and draft your own 5 questions. Start by picking a health outcome you genuinely care about. Maybe it is asthma in the city where you grew up, or missed prenatal appointments, or dental care deserts. Any place-based health problem works. Now, write 1 sentence for each of the 5 questions. For the what, name the measurable outcome worth improving, and push yourself to say why improving it delivers a societal or financial benefit. For the where, describe what data could show you the concentration. Would you geocode utilization records? Would you map hospitalizations? For the who, list 2 or 3 population characteristics you would want to examine within the high burden areas, things like vehicle access or comorbidities. For the why, propose 1 plausible mechanism and try to name which framework it comes from. Is it an enabling factor from Anderson? An accessibility problem from Penchansky and Thomas? For the how, take your best guess at a historical policy that might have shaped the pattern. You do not need to be right. You need to be thinking in the right direction. When you finish, read your 5 sentences in order and listen for the story they tell. If the sequence flows, you have just sketched the spine of a geospatial research project. If a sentence feels forced, that is useful too. It shows you where your design needs more exploration. Resume when you are ready, and we will test your grasp of the protocol with a knowledge check. Let us check your understanding of the protocol with 2 questions. Here is the first. A researcher has specified a model grounded in Anderson's behavioral model and is now hypothetically modifying travel time to estimate what would happen if a geographic barrier were removed. Which of the 5 stages is this researcher working in? Pause for a moment and commit to an answer. Ready? This is the why stage. the home of counterfactual what-if scenarios, where the frameworks ground the model and the counterfactual rehearses the intervention before it is attempted. If you said the how stage, remember the direction of the gaze. The how stage looks backward at historical policies. The why stage looks forward at hypothetical modifications. Here is the second question. In the where stage, the chapter insists that visualization should occur at multiple scales. Why? Think about what changes as you zoom in and out. The answer is that aggregation and disaggregation can mask the variation of interest. A burden invisible at the county level may be stark at the neighborhood level, so a single scale can hide the very pattern your study needs. If you got both questions right, you have the protocol firmly in hand, and you are ready for the chapter's next warning. Even a well-designed project can go wrong at the moment of interpretation. The next section introduces the fallacies that lie in wait. You now know how to design a geospatial research project. This section is about how to avoid breaking one. Spatial research comes with its own family of fallacies, errors that arise from geography itself and do not exist in ordinary study designs. The chapter names four: the ecological fallacy, the atomistic fallacy, the modifiable areal unit problem, and edge effects. Some are interpretation errors, mistakes made after the analysis is done. Others are specification errors, baked into how you defined your units in the first place. And the chapter offers a warning worth taking personally. These fallacies are not intuitive to those untrained in spatial methods, which means smart, careful researchers commit them all the time. Recognizing them is the first line of defense. Navigating them is the second. We will do both, starting with the full table of hazards. Here are all four fallacies side by side, and instead of reading every cell, I want you to study the architecture of this table. Look at the symmetry in the first two rows. The ecological fallacy interprets data below the unit of analysis, and the atomistic fallacy interprets data above it. Same error mechanism, opposite direction. One infers downward, the other infers upward, and both cross a scale boundary the analysis cannot support. Now look at the bottom two rows and notice that they are different in kind. The modifiable areal unit problem, which the field shortens to MAUP, and edge effects are not about how you interpret finished results. They live inside the design itself, in how the boundaries were drawn and what those boundaries assume about the people near them. So the table splits neatly. 2 interpretation errors on top, 2 design problems below. Hold on to that split because it determines the defense. Interpretation errors are cured by discipline in what you claim. Design problems are cured by engineering choices in how you build the study. Over the next 4 slides, we take each fallacy in turn, starting at the top with the ecological fallacy. The ecological fallacy comes first because it is the one you are most likely to commit without noticing. Here is the key insight. The ecological fallacy is an interpretation error, not a direct result of the analysis. Your model can be perfectly estimated, your data spotless, and you can still commit this fallacy in the final paragraph of your paper. The error is extending area-level results to individuals. Suppose your neighborhood-level analysis shows that areas with longer travel times have worse diabetes management. It feels natural to conclude that any individual with a long travel time manages their diabetes poorly. That step down from area to individual is exactly the forbidden move. Why is it so dangerous? Because of a phenomenon called Simpson's paradox, where results can potentially reverse directionality depending on aggregation. A relationship that is positive at the area level can be negative at the individual level within the very same data. Not just weaker, reversed. Let me slow down and make that concrete. Imagine that within each high-burden neighborhood, the individuals who travel farthest are actually the ones managing their diabetes best, perhaps because the people able to make long journeys are those with vehicles, family caretakers, or fewer mobility-limiting conditions. Aggregate the data, and the neighborhood's overall burden dominates the picture. Disaggregate it, and the individual pattern points the other way. Same data, two scales, two opposite conclusions. And the stakes are not academic. The chapter spells out the consequence. If the fallacy is not caught, resources dedicated to overcoming geographic barriers are not properly allocated, resulting in an unfilled gap in care access. An intervention aimed at the wrong people leaves the community's true need unmet. The defense is simple to state and demands real discipline to practice. Keep inferences at the analysis unit of scale. If you analyze neighborhoods, conclude about neighborhoods. The next fallacy shares the same error mechanism, but it runs in the opposite direction. Instead of inferring downward, it infers upward. The atomistic fallacy is the ecological fallacy standing on its head. Where the ecological fallacy inferred downward from areas to individuals, the atomistic fallacy makes inferences from a smaller unit to a larger unit, and it produces the same cross-scale error in the opposite direction. Why can you not simply scale small findings up? Sometimes you can. The chapter concedes that certain cases allow small units to aggregate neatly into larger ones. Census blocks, for example, are designed to nest inside tracts, but other boundaries refuse to cooperate. The chapter's example is congressional districts, which do not cleanly aggregate from the smaller units you may have analyzed. District lines cut across neighborhoods and communities in ways that make any upward inference structurally unsound. And the atomistic fallacy carries a specific, predictable distortion. It produces an overestimation of need. Here is the mechanism. When you project a small unit's finding onto a larger unit, you implicitly assume the distribution is uniform across that larger unit. You studied one high-burden neighborhood, and you conclude the whole district shares that burden. But the true distribution across the larger unit is non-uniform. The burden is concentrated in the pocket you happen to study, and much of the district may look nothing like it. Your upward inference paints the entire district with the neighborhood's need, inflating the apparent problem. The defense, the chapter says, is like the ecological fallacy's defense, because this too is by nature an interpretation error. Keep your claims at the scale you analyzed. Both of these fallacies are mistakes of inference made after the model runs. The next fallacy is different. It lives inside the model's specification itself. We said earlier that spatial research differentiates itself by incorporating geography directly into the model's specification. The modifiable aerial unit problem, or MAUP, is the price of that move. When you operationalize geographic scale and boundaries, you face a trade-off, an unavoidable discussion over unit size and where the boundary lines fall. The uncomfortable truth is that your results depend on those choices. Draw the zones one way and an effect appears. Draw them another way and it fades. Now, be careful to distinguish MAUP from what we have already discussed. This problem is different from simple aggregation or disaggregation transformations, the zooming in and out we covered in the where stage. MAUP is essentially redistricting geographic units, redrawing the lines so that the same territory is carved into different zone compositions. When the lines move, people and facilities that used to share a zone become separated, and strangers become zone mates. The composition of every unit changes, and with it, every statistic you compute. Picture a cluster of residents with poor diabetes management sitting near the corner of 4 zones. Draw the map one way and the cluster lands inside a single zone, where its burden stands out sharply. Draw the map another way and the same cluster is split across all 4 zones, diluted until no single zone looks alarming. Nothing about the residents changed, only the lines did, and the lines decided whether their burden appears pronounced or masked. If results depend on lines that could reasonably have been drawn many ways, how do you trust any single map? The chapter's answer is the sensitivity analysis. Because of this recomposition problem, you assess how the estimated effect holds across different compositions and scales. Run the analysis under several defensible zoning schemes. If the effect survives every one of them, you have a robust finding. If it appears in only one particular carving of the map, you have learned something important and humbling about your result before a reviewer learns it for you. MAUP concerns the interior of your study area. The final fallacy concerns its edges and the people who live near them. The last fallacy is the most concrete of the 4, because it is about something everyone does. People travel. Edge effects become a problem in geospatial research when researchers do not account for the mobility of people within their geographic unit of interest. Your map draws a boundary around a market, and your model quietly assumes the people inside it seek care inside it. But specific to care access, patients have the option of going into a different market. A boundary that is solid ink on your map is, to the patient living beside it, nothing at all. Think about someone living near the edge of your study zone. The nearest clinic may be across the line, closer than anything in their assigned zone. Of course they cross. The crossing is not misbehavior. It is the rational response to geography, and a model that cannot see it is describing a world that does not exist. The chapter treats this as a serious design concern for how a market is districted, and here is the scenario that shows why. Patients in a low-supply market can utilize a neighboring market that is not experiencing scarcity. Now consider what your analysis reports if it cannot see that movement. The low-supply market looks like a crisis. Residents appear stranded with too few providers, but in reality, many of them are quietly receiving care next door. Your model, blind to the border crossing, overstates the gap. Recall the pattern across this whole section. The atomistic fallacy overestimated need through assumed uniformity. Edge effects overestimate need through assumed immobility. Both errors send resources toward gaps that are smaller than they appear, while communities with true gaps wait. Unlike the interpretation fallacies, though, edge effects can be engineered against, and the chapter gives us 3 concrete strategies. Those are next. The chapter offers 3 strategies for taming edge effects, each attacking the boundary problem from a different angle. The first strategy appends buffer zones beyond the administrative boundaries. Remember the buffer analysis from our techniques section? Here, it returns as a defensive tool. By extending data collection past the official study line, you capture the clinics and hospitals just outside it, the ones your border residents actually use. The boundary of your data becomes wider than the boundary of your claims. The second strategy is more radical. Instead of accepting a county line drawn for administrative convenience, you redefine the boundaries around how people actually move, using route or travel time logic from network analysis. A market defined by 30 minutes of real travel reflects patient behavior far better than a line on a political map. The third strategy is a compromise for when the original boundaries must stay. You weight the healthcare facilities near the border, discounting a clinic at the edge of your zone because it serves people on both sides, rather than counting its full capacity as if it served your zone exclusively. 3 strategies, 1 shared purpose, and the chapter states it plainly. These strategies reduce the likelihood of producing an analysis that overestimates need, so resources can best be distributed to areas with true gaps in care access. Let us practice spotting these hazards. Pause the presentation and try to diagnose 4 short scenarios. Take a minute with each before you resume for the answers. Scenario A. A research team analyzes diabetes outcomes at the county level and finds that counties with longer average travel times have worse outcomes. In the discussion section, they write that patients with long travel times fail to manage their diabetes. Which fallacy is that? Scenario B. A team completes an analysis using census tracts and finds a strong effect. A colleague redraws the study area into differently shaped zones of similar size, reruns the analysis, and the effect nearly vanishes. What problem has the colleague exposed? Scenario C. A team studies one high-burden neighborhood and then reports that the entire congressional district containing it shares the same level of need. Which fallacy and what distortion does it produce? Scenario D. A market with few providers looks like a crisis on your map, yet many residents near its boundary routinely receive care in the neighboring market, which is not experiencing scarcity. What is your analysis about to get wrong? Ready for the answers? Scenario A is the ecological fallacy, interpreting county results below the unit of analysis, and Simpson's paradox warns the individual relationship could even run the other way. Scenario B is the modifiable areal unit problem. The results changed as boundaries changed, and the colleague effectively performed the sensitivity analysis the original team skipped. Scenario C is the atomistic fallacy, inferring upward onto a district that does not aggregate cleanly and overestimating its need. And scenario D is edge effects. The model assumed people stay inside their assigned zone, so it overestimates the market's true gap in care. If you caught all four, excellent. One more check on this section, and then we move to data privacy. Two final questions before we leave the fallacies. First question. Your study's results might depend on how the geographic zones were drawn. What is the specific defense the chapter prescribes for the modifiable areal unit problem? Pause and answer. The defense is a sensitivity analysis. You assess how the estimated effect holds across different compositions and scales, and an effect that survives multiple reasonable zoning schemes is robust. Second question. Two of the four fallacies are described as interpretation errors rather than analysis errors, and they share essentially the same defense. Which two, and what is that defense? Pause again. The answer is the ecological fallacy and the atomistic fallacy. One interprets below the unit of analysis, the other above it. And because both are errors of inference rather than computation, the shared defense is discipline at the writing desk. Keep your inferences at the analysis unit of scale. And remember the thread that ties this section together. The atomistic fallacy and unhandled edge effects both overestimate need, and an overestimated gap pulls resources away from communities whose gaps are real. You have now completed the design and hazards portions of this lecture. Next, we turn to a responsibility that outweighs the analysis itself, protecting the people inside your data. We have covered the techniques, the frameworks, the design protocol, and the fallacies that can distort a spatial model. Everything so far has been about producing a rigorous analysis. This section is about the obligation you owe to the people inside your data. Location is one of the most identifying attributes a person has. Knowing where someone lives, combined with just a few other facts, can be enough to pick them out of a supposedly anonymous dataset. That means the very variable that makes your analysis meaningful is also the variable that puts your study population at risk. In this section, we walk through the trade-off between privacy and analytic granularity, and then through the layers of protection that regulate it. Those layers are the safe harbor method under the Health Insurance Portability and Accountability Act, the Institutional Review Board, and the expert determination pathway. Let us start with the trade-off itself. Here is the tension in its plainest form. There will always be a trade-off between data privacy and a meaningful geospatial analysis, because location data that is granular enough to be truly revealing is also granular enough to identify people. The chapter is unambiguous about how to resolve this tension. The obligation to privacy always outweighs the analysis. Always. But notice what that costs you. When you mask location data to protect individuals, you are obscuring the exact variation you set out to study. The differences between one block and the next, between one apartment complex and the clinic down the road, those differences are your findings. Blur them, and you blur the analysis. Think about what the blur does in practice. Aggregate your dual enrollees up to a large enough unit, and the block where nobody owns a car, the residential pocket cut off from its clinic by a highway, the long bus ride that decides whether an appointment gets kept, all of it averages away into a single number that describes everyone and explains no one. And here's the part I want you to sit with, because it is genuinely uncomfortable. The people you are protecting by masking the data are the same people who would benefit from the analysis at full resolution. That is the equity paradox at the heart of this chapter. The research working to fill an equity gap can become the very tool that deepens it, either by exposing a vulnerable community to re-identification or by producing an analysis too coarse to direct resources where they are needed. So what do? You design for privacy from the beginning rather than bolting it on at the end. The basic techniques you already know, buffer analysis, network analysis, and dissolve, become privacy tools. Aggregating point data into larger units, or replacing exact addresses with travel time measures, preserves analytic meaning while protecting individuals. And beyond your own design choices, regulation provides a floor. That floor is the safe harbor method, and it is where we go next. The first layer of protection comes from the Health Insurance Portability and Accountability Act, which most of us simply call HIPAA. HIPAA offers a method called safe harbor, and the idea is straightforward. You remove 18 specific identifiers from the dataset, things that could tie a record back to a person, and by removing them, you reduce the likelihood that anyone can re-identify the individuals inside. For most health research, that feels like enough. For spatial research, it is not, and I want to walk you through exactly why, step by step. Step 1. Your de-identified dataset still carries location in some form, because location is the whole point of the study. Step 2. Somewhere outside your control sits an external dataset that contains identified individuals, people with names attached, living in those same places. Step 3. Think back to the spatial join, one of the foundational techniques from earlier in this lecture. A spatial join combines two separate datasets using location as the common key. That is precisely the mechanism an adversary can run in reverse. Join your de-identified records to the external identified records through their shared geography, and the individuals you carefully de-identified can lose their privacy protections entirely. This is what the chapter means by reverse data engineering, and notice the uncomfortable symmetry in it. The same technique you use to enrich your data is the technique that can expose your participants. And the chapter tells us to adopt a specific posture here. Assume that bad agents exist, and that they would exploit re-identification for discriminatory practices. Under that assumption, Safe harbor is not a fortress. It is a baseline, the minimum standard, the floor beneath which you must never fall, but upon which you should never solely rely. So if the regulation alone is not enough, who else is watching? That brings us to the second layer of protection, the Institutional Review Board. The second layer of protection is the Institutional Review Board, or IRB. The IRB's job is to conduct a risk-benefit analysis of your study design. It weighs the potential harm to participants against the potential value of the knowledge produced, and it oversees the ethics of how you treat your target population. This is a genuinely important safeguard, and nothing I say next diminishes that. But the chapter raises a caution that surprises many students. An IRB may not include anyone with expertise in geospatial research. Board members are typically drawn from clinical, behavioral, and biomedical backgrounds. The specific technical question of whether de-identified data can be re-identified through spatial methods may simply never come up in review, and that creates a sobering possibility. Your study can receive full IRB approval and still carry a critical vulnerability because nobody in the room knew to look for it. The responsible move then falls to you as the researcher. When your board lacks geospatial expertise, seek input from a geospatial expert yourself. That added perspective evaluates the technical mechanics of re-identification, which matters enormously for vulnerable populations. Consider our dual enrollees. In some geographic units, only a handful of people are enrolled in both Medicare and Medicaid. When a population is that sparse, even aggregated data can point to specific individuals. Low density is itself a privacy risk, and there is a practical bonus to bringing in outside expertise. That same expert can certify your design through a second HIPAA pathway, one built for exactly the situations where Safe Harbor's fixed rules would force you to suppress the small cells your analysis depends on. That pathway is expert determination. Expert determination is the second pathway to HIPAA compliance, and it works very differently from Safe Harbor. Instead of applying a fixed list of removals to every dataset, regardless of context, a qualified expert conducts an independent review of your specific study and certifies that its design carries a low risk of re-identification. Hold those two ideas side by side because the contrast is the whole lesson. Safe Harbor is a fixed rule. It applies the same list of removals to every study, no matter how sparse the population, no matter how revealing the geography, and no matter what the analysis actually needs. Expert determination is a tailored evaluation. It looks at your actual data, your actual population, your actual geography, and asks what protections this particular study needs. That tailoring is what lets the analysis keep its meaning, and it matters most in exactly the situation this chapter cares about, working with data that would normally require small cell suppression, where a fixed rule would force you to erase the sparse geographic units where vulnerable dual enrollees actually live. The expert refines the study so that a geospatial project built to close an equity gap does not unintentionally become a reason the gap widens. But the chapter does not let us celebrate this pathway without noticing something bitter about it. The pathway that best serves equity is itself inequitable. Hiring a qualified expert costs money. Not every researcher has grant funding that stretches that far, and those who cannot afford the tailored review are forced into the Safe Harbor method by default. So the well-funded study preserves its granularity and its statistical power, while the underfunded study, quite possibly serving the community with the greatest need, must blur its data to comply. Keep that irony in mind whenever you budget a geospatial project. The cost of an expert review is not a luxury line item. It may be the difference between an analysis that serves its community and one that cannot. Let me close this section with a sentence from the chapter that I most want you to carry into your own work. Both pathways reduce risk, but it is up to the principal investigator to handle the residuals of risk through intentional design choices. Read that carefully. Both pathways reduce risk. Neither eliminates it. Safe Harbor strips 18 identifiers, and re-identification through spatial joins remains conceivable. Expert determination tailors the protections, and some residual exposure still survives the certification. Compliance is not the same thing as safety. When the paperwork is signed and the approvals are filed, whatever risk remains does not evaporate. It transfers to you, and the chapter names the instrument you have for managing it: intentional design choices. Choosing to aggregate before you must. Choosing travel time over street address when travel time answers the question. Choosing to run your sensitivity analysis before an adversary runs theirs. Every one of those choices is a small act of protection that no regulation required of you. This is why I said at the start of the section that privacy is a design constraint and not an afterthought. You cannot certify privacy into a finished study. You can only design it in from the beginning. With the ethical foundation in place, we are finally ready to watch everything in this lecture come together. But first, a quick knowledge check on what we just covered. Time to check your understanding of the privacy material. 2 questions are on the slide. Pause the presentation, think each one through, and then resume for the answers. Question 1. Your dataset has passed the Safe Harbor method. All 18 identifiers are gone. Why might your participants still be identifiable? If you need a cue, think back to the foundational technique that combines 2 datasets through location. Take your time. Here is the confirmation. A spatial join with an external identified dataset can restore identity through shared geography. That is reverse data engineering, and it is why the chapter treats Safe Harbor as a baseline rather than a guarantee. Give yourself extra credit if you also remembered that low-density geographic units carry their own risk, because even aggregated numbers can point at specific people when only a few dual enrollees live in a unit. Question 2. What does the expert determination pathway offer that Safe Harbor cannot, and what limits access to it? The cue here is fixed rule versus tailored evaluation. Here is the confirmation. Expert determination tailors the protections to your specific study, which can preserve the granularity and statistical power that Safe Harbor would otherwise suppress. The limit is funding, and that is the irony the chapter asks you to sit with. If both answers came easily, you are ready for the case study, where every piece of this lecture finally operates together. Here's the chapter's closing argument, and by now, every clause of it should feel earned. Geospatial research is its own methodological approach, differentiating itself through its unique techniques, its unique fallacies, and its unique data privacy concerns. You have toured all 3. The fundamental shift in thinking is to address area-based variables within a model's specification, so the model accounts for the underlying mechanisms that drive geographic disparities. Location moves from a passive attribute of your study population to an active, specified driver of the outcome. That single shift is the chapter in one sentence. There are many ways to design and structure such a project, but the requirements always revolve around the same 3 constants: problem definition, framework selection, and a justification for every design choice. And designing a study under those requirements forces the researcher to challenge their own assumptions through reflexive journaling, a written record of challenged assumptions that creates the transparency transdisciplinary collaborators and reviewers need. And that record is how the researcher produces scholarship that is defensible, grounded in multiple perspectives, and robust enough to handle alternative claims. The chapter's main takeaway comes with exactly 2 reasons, and I want you to be able to recite both. Geospatial research is by design a collaborative and iterative process. First, because transdisciplinary communication assists with clarifying the theoretical significance of area-based variables. And second, because that same process of communication helps identify vulnerabilities before bad actors can exploit them. Better science and safer science from the same habit of talking across disciplines. The end point of all of it is translation, turning geospatial findings into policy-relevant recommendations that advance equitable access to care, so that the analysis returns something of value to the community that made it possible. 2 recap slides and 1 closing thought remain. Before we finish, let us file this chapter where it belongs, inside health economics. 5 concepts from your home discipline did the quiet structural work throughout this lecture. First, health behavior utilization, carried by the idea of bounded rationality. Patients decide where to seek care with limited information, limited time, and limited experience, which is why 2 identically insured dual enrollees with objectively equal access can utilize care completely differently. That single idea explained why equal access on the map never guarantees equal utilization in practice, and why interventions must adapt to what patients perceive as available and acceptable. Second, Anderson's behavioral model, which conceptualizes healthcare access as a function of predisposing factors, enabling resources, and need. For spatial work, the enabling resources mattered most, because they are what the built environment either provides or withholds. Third, the framework of Pinchansky and Thomas, which conceptualizes utilization as a function of fit between the patient and the healthcare system across availability, accessibility, accommodation, affordability, and acceptability. Fourth, market scarcity. The chapter framed geographic disparity as a market distribution issue, where providers concentrate in some markets and thin out in others, and dual enrollees, precisely because of their financial constraints, may not be able to live near the markets where care is plentiful. Scarcity they cannot relocate away from. And fifth, time cost, which the chapter framed in several forms to make one point. The cost of reaching care depends on the mode of transportation available, whether the price is paid metabolically by walking, in gasoline by driving, or in fares and waiting by public transit. Distance is one number, but its cost varies by who is traveling. Hold on to these 5, because they are the vocabulary your future geospatial work will share with the rest of this book. One last look at the take-home points. We saw these 5 take-home points in the opening minutes of this lecture when they were promises. Now they are summaries. First, every community has its own unique story of health disparities, and researchers use geographic factors to make those lived experiences tangible and quantifiable. Second, think beyond singular straight lines. Miles to a hospital may not encapsulate someone's journey when traffic, transportation cost, and land use all intervene. That was the story of our 2 identical individuals and of network analysis. Third, researchers combining geographic factors with health data must be well versed in small cell suppression and geomasking, because spatial data generates new risks of reverse data engineering that can identify the patients in your study. Fourth, hold a healthy negotiation between data granularity and data privacy, so the analysis stays meaningful while the population stays protected. You watched that negotiation resolve through the expert determination pathway. And fifth, The goal of a geospatial research project is to illustrate how a community is impacted by its built environment, so that interventions gain place-based specificity, like mobile clinics routed to where travel time predicts diabetic crises. Your final exercise is a reflection. Imagine defending your own study design before a review board. Which single design choice, your scale, your privacy pathway, your framework, would you defend first, and what would you say? Pause and sketch your answer. Then join me for the closing slide. You have reached the end of the session, so let me bring us back to where we began. 2 hours ago, distance was a number, a count of miles between a patient and a hospital. You now know it is nothing of the sort. It is traffic and bus fare, redlined history and inherited neighborhoods, perceived options bounded by experience, and privacy risk encoded in coordinates. Along the way, you built a toolbox, buffers and networks, joins and dissolves, overlays and choropleth maps, and you learned that the story only emerges when those techniques are combined. You learn 3 frameworks that move you from broad determinants to measurable dimensions to the bounded rationality that shapes what patients actually do. You learn to structure a project around 5 questions, to guard your interpretations against 4 fallacies, and to carry the obligation of privacy through every design choice. Because the obligation to the people inside the data always outweighs the analysis. This chapter asked one shift of you. Treat place as a mechanism, specified in the model, interrogated for fallacies, and protected in the data. Do that, and every project you design will carry the same 3 constants this lecture kept returning to: a problem worth solving, a framework that grounds it, and a justification for every choice you make along the way. If you want to go deeper, the chapter itself is your next stop, and the frameworks and methods you met today will meet you there. Communities are already telling their stories through geography. You are now equipped to listen rigorously and to answer with interventions that know exactly where they are needed. Thank you.